Welcome back to CS353 Makeup Week. We're going to be covering, starting with physical addresses and words 10.14 here today. So we divide bits of memory up into blocks and bits each, and then we basically call each of those blocks a word. And if you were to look at the figure on page 150, you would see this, where basically each physical address is broken up into a word. So word 0, 1, 2, 3, 4, 5. And there's another bit of terminology as the width of the word. That's also known as the word size. So for example, 32 bits, 64 bits. And a computer is sometimes characterized by its word size. So for example, I'm running on a 64-bit computer now. In the previous generation, there were mostly 32-bit computers, but now we're at in the 64-bit generation. So that is what is referred to when you say you've got a 64-bit computer. Basically, you've just got a bigger word size. Therefore, you can hold more in that one particular grouping of memory. That one particular bit of memory can hold more. So each word of memory is assigned a number called the physical memory address. And underneath we view this physical memory as an array of words. Now one thing to note is that hardware must transfer an entire word. So even if the word is not being, even if the full word is not going to be used, we have to transfer the whole word. That is both a blessing and a curse. Most times, as we've talked about already, most times the program that is running, the instructions will be very close to each other, and therefore it's going to need the entire word anyway, so it's fine that you can sort of read it all in at once. But sometimes you'll read in some unnecessary data, and you'll just sort of ignore that. As I said, this is kind of a depiction of some physical memory properties. So read or write operations apply to the entire word, and you have to write to the entire word as well. So there's a trade-off that exists here. If we have a larger word size, we have higher performance, because basically we have more memory that we can read in. But we do have more parallel wires and circuitry that we have to do, and it's a higher cost. That's why 64-bit really hasn't become popular until now. And lastly, the architect has to design all parts of the computer to basically account for what the size is for the word, and that goes for how it treats integers and floating point numbers, etc. And when you see assembly languages, for example, you'll talk about how, for example, the assembly language we're using is Intel 64-bit, but it still uses some elements of 32-bit. In fact, the lower half of, when you look at like the EAX register versus the RAX, the EAX is the lower half of that, the 32 bits. Byte addressing is the view of memory presented to the processor. So each byte is assigned an address. This makes it convenient for programmers. So we have a physical address that's assigned to each byte of memory. Bytes of memory are generally 8 bits, as you know. So basically that one section of 8 bytes is assigned a physical address, and then we can refer to that physical address as programmers. Then we do a basic translation between byte and the word address, and that is what's performed by the memory controller. So we can use byte addressing, but the physical memory can use word addressing. So underneath, word addressing is used because that's what is more efficient to be used on the physical side. But up top, as programmers, we can use byte addressing. Byte addressing allows us to refer to just one byte, for example. It's very rare that we have to refer to a bit, for example. So more often we'll refer to a byte, and we'll actually use byte addressing. And if we do want to refer to a bit, we can, of course, but we just need to, refer to like an offset of a byte, basically. Here's a typical address translation scheme. This is a 32-bit physical word, 4 8-bit bytes per word, and we number those sequentially. So bytes 0, 1, 2, and 3 go into physical address 0. So if you wanted to access byte 2, you would access physical address 0. So you would load up address 0 and have an offset into it that gets you to the byte number 2. So the offset is given by b mod n, where the word address is w equals b over n. So if we have n equals 4, byte address of 11, that would translate to a word address of 2 with an offset of 11. So again, 11 is a word address of 2, an offset of 0, 1, 2, 3. That is what 11 represents. To be efficient, we usually choose word size as a power of 2. This way, when we're extracting the word address, we can just simply extract the higher order bits, and that's our word address. And then the offset is computed by extracting the lower order bits. So instead of doing division, which is a costly thing that requires an ALU, if we do these by powers of 2, we can simply just chop off the bottom half, and that gives us our physical address, our word address that we're going to be looking at, and then the rest of those lower order bits can refer to the offset that we're looking at. So again, arithmetic calculations such as division and remainder, to avoid those we can use the power of 2, and this is what that ends up looking like. So the word address is given here. The entire byte address is b, so that's 17 bits. The word address is given as 4 with an offset of 1. So the whole byte address is 17, but the word address in this particular word is 4. So if you compare that to here, 17 word address is 4, bit is 1, and we see offset of 1 indeed to be the case. So we're just chopping off this section of it to get the word address, and then we're chopping off this other section to get the offset. And you can compare that if you want to the example on page 152, which is over here, to see how that actually works. So for byte alignment, this is an important part of for programmers to consider, is that the integer storage in memory, it can help to know that, for example, an integer that's composed by bits 12, 13, 14, 15 is aligned, but maybe 6, 7, 8, and 9 is not aligned in this case. So this organization of memory actually affects programming. So if we do allow for an aligned memory access, it should be possible at least to get improved performance if programmers align by word addressing. So the question is, how large can memory be? Memory size isn't only an economic issue, it's more, it is an economic issue, but it's also known as a aspect that affects hardware, and it's inherently linked to other choices like the addressing scheme and whatnot. So for example, a system that uses 32-bit integers uses 32-bit addresses. These choices end up being very important for the rest of the system. So the size of the address limits the maximum memory. So if we've got a 32-bit address, we can represent 2 to the 32nd unique addresses, and that's what we call our addressing space. So if we want to obtain a single byte, what we would have to do is fetch the word from memory and extract the word from that byte. And we'll see an example of that in C in a second here. To store the byte, we'd fetch it from memory, replace the word, and write it back to memory. And we've done that a couple times in class in our assembly examples. Oh, they don't have an example on these slides. Let me show you quickly what that ends up looking like. Basically, you would have, say you've got W as the word. You can shift that by 24 bits and it with we want to get the leftmost byte from this 32-bit word, so we're doing 24 bits, and then the rest that'll be left over is the last byte, because that's the last 8 bits. So we're going to AND that together with 0xFF. And that's a C statement that'll give us the leftmost byte from that 32-bit word. As far as measuring physical memory size, we can organize the set of M words that each contain N bytes, and that way we make a controller hardware efficient, because M and N are going to be chosen to be powers of 2. And then that means that memory sizes are usually expressed by powers of 2, and that is why memory sizes, by the way, are expressed as powers of 2. So you might have wondered why 1024, for example, is a kilobyte, or a megabyte being 2 to the 20th. So speeds of data networks are usually expressed in powers of 10, so a gigabit internet is 10 to the 9th per second. But just keep in mind that that's a difference between storage and transmission speed. That's usually just the speed that's represented by like a gigabit internet. That doesn't necessarily refer to the same thing we think about when we think about megabytes and gigabytes. A gigabit internet is 10 to the 9th, as opposed to a power of having 2 raised to a power of something, as we see with kilobytes and megabytes, and as well gigabytes. So in C, you can actually directly access memory. It's got this heritage basically of allowing for both byte and address and word addressing. So if you want to increment by 4 bytes, you could do an IPTR++, and that will increment by 4, because an integer is size 4 bytes. Memory dumps are something that's very useful, and you occasionally get those in practice when you'll be working in real life programming. You may not get a full call stack, but you might get a memory dump. And what you can do with memory dumps is you can actually translate those into values and see where the program crashed and what the values were at the time of the crash. And each line of output would basically be specifying memory address and the bytes that are at that address. So here's an example memory dump. The address column is giving the memory address of the leftmost byte of that line, and the values are shown in hexadecimal. So the head of that linked list that is responsible for the memory list is found at 0x0001BDEF, or E4, and that's the first line of the dump that we see on here. And then we see the contents of that memory location as well. So the first node at 1BDF8 contains 192, which is 0xC0. So that's how you get the number 192 at that particular memory location. Here's the second node showing that it's the number 200. So there's, and then of course the last node at BE00 contains 100, or 0x64. Okay. So basically, just assume that this is sort of how that works. And that's just assuming that the head is located at that particular location. And then we've got basically a count and a next pointer. I'm almost done. So 2 major techniques in increasing memory performance are memory banks and interleaving. I believe we can employ these as parallel hardware. Memory banks are an alternative to single memory and a single memory controller. This way, the processor connects to multiple controllers and each controller connects to separate physical memory. This is the way that looks. I actually don't have a picture of this particular method. What I do have is another slide that basically talks a little bit more about memory banks. There's a transparent way that basically we can use the hardware to find and exploit where the particular actual reference is between the two different memory banks. The locations are being stored in one of two possible locations. And the opaque method is visible, and programs have to place items in those exact memory bank locations. Interleaving is more popular. This is related to memory banks. It's transparent to the programmer. It uses hardware to place into a certain location, so the requests go through an interface basically. And we use the lower order bits to choose the handle. So this is finally now to the picture I wanted to show you, where basically 0, 1, 2, and 3 are each stored in separate modules. 4, 5, 6, and 7 are in separate, and the interface is responsible for showing where those actually are. The higher performance that's allowed in this case is because we allow hardware to simultaneously access multiple memory items. This means that we can be accessing item 0 and item 2 at the same time without having to swap them in and out. The CAM is also known as the Content Addressable Memory. This is combining two key ideas, which is technology and organization. It includes parallel hardware for high-speed searches. If we think of all our memory as a two-dimensional array, we can call the array a slot, and then we can use special hardware to determine if X is stored in any row of the actual CAM, and we can operate this in parallel. So we can query each one of these slots in parallel. So here's a slot that's being queried. So it's providing a memory technology and an organization for the memory. So CAM is presented with a key for the lookup. The hardware searches the slot to determine if the key is present, and these searches can be performed in parallel on all slots at the same time, since that's how the hardware is structured. But also, since that's how the hardware is structured, this is what makes CAM expensive, because it has to be organized in that fashion. Partial match searching is possible. In this case, it's known as a ternary CAM. Each bin and slot can have 0, 1, or don't care. TCAM is simply going to ignore the don't care bits and can either report if it has a match or if it's all a complete match. So that is it for Chapter 10. The next video is going to be concerning Chapter 11, where we will be talking about virtual memory technologies and virtual addressing.